So this video is continuing with examples of doing problems or thinking about kinematics in one dimension with derivatives in time. So in particular, it's d by dt. All right. So first example is going to be very simple. What if x of t is simply constant in time? So I'm going to give it the value 4 meters. So 4 meters is the value of the position for all times. There is no time dependence. So secretly, you know that it is true that the position is 4 meters for any time because the function is sort of, how do you say it? Like, it's the simplest version of being dependent on a variable is to not be dependent on it at all. So you can see there's no dependence on time. So for all time. So if you think about it just with language, this means that for all time, the object is not ever going to be located anywhere else. So it is not moving. And so not moving means that its velocity is going to be 0, right? So not moving means that the velocity is 0 all the time, though. So, but let's look at this with our little derivatives and thinking about velocity and acceleration. So the velocity as a function of time is the time derivative of x of t. So this is generically true. My x of t for this particular problem is this ultra simple, kind of boring example, but let's take its derivative. So the thing you know in calculus is the derivative is going to hit everything inside of those parentheses. So the derivative on 4 meters, this is kind of stupid, but I think it's illustrative in a way. So, you know, the derivative of a product is the derivative of the first thing, which is a 4. So it's the derivative of a 4, and you multiply it by the meter. That's the second thing. So the derivative of a product is the derivative of the first times the second, plus the derivative of the second times the first, right? It's the product rule. So it's the meter times the time derivative of the number 4 plus the number 4 times the time derivative of the unit called the meter. And the reason I'm doing this is because I'd like you to see that the time derivative is very serious. Like the mathematical thing of doing the time derivative is it's a mathematical thing, and you have to follow all the math rules. And what I'm taking the derivative of is the product of two things, and I am checking or asking what is the time rate of change of that product. So fully checking, it's the meter times the time derivative of the number 4 plus the 4 times the time derivative of the unit called the meter. And so if you look at the first term is the meter times, so the number 4 just doesn't change in time. So there's no physical reason to think that the value of the number 4 ever changes. So it'll be the meter times 0, and 0 times the meter is a 0, so that's the first term. Plus the second term is 4 times the time rate of change of the unit called the meter. So it's kind of interesting to ask, does the idea of the meter change in time? And so it's kind of a stupid question in a way. It does not change in time, so it's got no time derivative. And so the answer is, if I take the time derivative of something that does not change in time in any way, then the value of the time derivative is 0. There is no change for as long as you want to wait. So it's a 0. So what does this mean, though? It means two things. It means that the object in question has the value of velocity of 0, so it is not moving, so it is at rest. But what's more is it's at rest for all time, because there's no explicit time dependence even though I have a time dependent function. So it's at rest all the time. Yeah, so it's at rest and it remains at rest. So if it's at rest and it doesn't change from that, then we already know the answer to asking what is the acceleration of this thing. So again, this is an ultra simple example. So you already know, just in the language, if it's at rest and that never changes, then if what the acceleration describes to me is how the velocity is changing, well, I already know the answer. It's not changing. The velocity is just not changing. It is 0 and it just stays 0. It remains at rest for all time. But let's check the calculus. So checking the calculus is taking the time derivative of the function v of t. But we just found up here that v of t is just the function 0. So it's kind of silly, but we're about to take the time derivative of 0 and we'll get 0, of course. So yeah, but we already guessed it. And so you sort of, at the same time, you're keeping track of the sort of conceptual thinking about relationships between how you're moving and how you are changing your location or translating, as well as how the velocity is changing in time. In this case, the velocity was remaining a certain value. So whenever the velocity remains a certain value and doesn't change, that means that the acceleration has value 0. Okay, so stupid example. Let me write the word stupid. But I think there's actually a lot to learn in that stupid example. So let's move on to a more complicated example that's still quite simple. So what if we said that, so this is another example, what if we said that x of t was actually, I'm going to describe it as linear. It's a linear function of time. So linear function of time. So I have an example. So I'm going to say that x of t equals 3 meters and then minus 2 meters per second times t. So linear functions are functions such that the variable only shows up with a first power and then also a constant. So a constant plus a slope times the variable. So it kind of looks like y equals to mx plus b, like a straight line. So it's a linear function of time, straight line function of time. If you were to draw x of t in time, t, at t equals to 0, if you put 0 here, x of 0 is just 3 meters. So if this is the t equals to 0, it starts off at 3 meters. So that's the y-intercept. And then I've got a slope of -2. And so this is a picture of the position as a function of time. It starts off at the location, here's 0, here is 3 meters. It starts off here and at 2 meters per second drifts towards the left. And it does that constantly, or linear in time. So I've got a line in time for position as a function of time. So let's ask the question, what is the position at the value 0 for time t? So you just take 0 and you plug it in, and the only place it goes is right here. So 0 times whatever this is, that whole term is 0, and I'm just left over with 3 meters. And the idea here, what I'm trying to show you, is that's the origin often of claiming what's referred to as an initial position. That is, x at 0 gets this special name, x sub 0. It's just the evaluation of the position at the initial time. And that initial position, I showed it here, and I showed it here. That's the position at t equals to 0 seconds. All right, so that thing that stands right there, I could call it x naught. So sometimes this is called x, N-A-U-G-H-T, naught. So that's the naught. Okay, so, but let's do some calculus. So v of t is d by dt of x of t. So I go and I take the time derivative. So d by dt of the thing, 3 meters minus 2 meters per second times the time t, like this. So earlier, I was super pedantic. I was super deliberate about taking the derivative. And the derivative of the product of two constants was just 0. It turned out to be 0. But you could have guessed that from the very beginning. You sort of knew that that 4 times the meter was a constant value that has no time derivative, or its time derivative is 0. So back over here, this is the time derivative of a summation, and that time derivative can act on all the parts of the summation, and you just add it all together. So what I mean by that is this is d by dt of 3 meters, and then plus d by dt of the second term. The second term is that minus sign, 2 meters per second times the time t, like this. And so the derivative of this square bracket is the sum of those two derivatives there. The derivative of the first thing is 0. I hope you agree with me. The derivative of the second thing, though, everything in front of the t is like a constant coefficient on the variable t. And I think you know enough calculus for me to just be able to say that this is minus 2 meters per second. Because the time derivative of t is 1. It has value 1. So maybe I'll just put that 1 explicitly. So this 1 is d by dt of t. And the negative 2 meters per second just stays along for the ride. So I'll finish it and write 2 meters per second. So no explicit time dependence. So what this means is that v of t is constant. That is, it does not change in time. There is no time dependence. It's got a fixed value. Quite honestly, it's a fixed value in the same sense that the earlier example, the velocity has a fixed value of 0, a fixed value of staying still. But in this case, it's got a fixed value of moving with this constant speed. Oh, and I blew it. I made a mistake. I forgot to bring along that minus sign. I'm sorry. Yeah. So it's this constant value of negative 2 meters per second. So you might ask, well, what is v at 0? What is the velocity at time t equal to 0? Well, it's the same as the velocity at any other time because there is no time dependence. It's this constant value. It's got this value, negative 2 meters per second. And a quick shorthand is to say that the initial velocity, the velocity that we start with at t equals to 0, has the value minus 2 meters per second, like this. Very quickly, to finish this example, it's kind of obvious, but can you see that a of t, which is the time derivative of this function right here, is 0? All right,